What specific problem does your method aim to solve regarding the evaluation of long context capabilities in large language models?
Our method aims to address the inadequacies in current evaluations of long context capabilities in large language models, LLMs, specifically focusing on three key limitations: performance saturation in retrieval tasks, limited context length in benchmarks, and a lack of granular insights from existing evaluations. We identify that many benchmarks primarily assess simple retrieval tasks, leading to performance saturation with little room for meaningful insights. Additionally, most evaluations are constrained to sub-100K contexts, which do not fully utilize the capabilities of frontier models that can handle much larger contexts. To overcome these issues, we design a series of challenging retrieval-based long context experiments, including novel multi-step threading tasks, and introduce a task-specific effective context limit metric that provides a more accurate assessment of model performance across varying context sizes. This approach allows us to better understand how LLMs navigate and utilize their long context capabilities.
Can you explain in detail how the proposed multi-threading retrieval tasks work? Please illustrate the step-by-step methodology used in these tasks, including any unique components introduced.
The proposed multi-threading retrieval tasks involve evaluating the ability of large language models, LLMs, to simultaneously retrieve final values from multiple threads of information. The methodology begins by modifying the haystack of key-value pairs to include more than one thread, where each thread consists of a sequence of linked keys. The models are tasked with determining the final value of each thread, given only the starting keys. Specifically, the experiments test various thread lengths 2, 3, 4, 5, 10 across different numbers of threads 2, 3, 4, 5, and investigate the effect of thread direction, whether all threads move forward, backward, or in random directions. A unique component introduced in this task is the assessment of thread safety, which evaluates whether the model's performance degrades when following multiple threads simultaneously. The results indicate that most models maintain consistent performance across different thread counts, suggesting they are thread safe, with notable models like Claude 3.5 Sonnet showing no performance degradation even with up to 25 threads.
Could you provide a simple example demonstrating how a single-threaded retrieval task is executed within your framework? Walk through the process from input to output, explaining any significant interactions.
In our framework, a single-threaded retrieval task begins with the creation of a haystack, which is a set of key-value pairs represented as JSON objects. For example, if we have a haystack containing keys like key 1, key 2, and key 3, the task is to retrieve the value corresponding to a specified key, say key 2. The model processes the input by identifying the position of key 2 inches within the haystack and retrieves its associated value. During this process, the model's performance is evaluated based on its accuracy in locating the key and returning the correct value, with the task's difficulty influenced by the context length. Notably, as context length increases, we observe a general decline in retrieval accuracy, indicating that the effective context limit for accurate retrieval is often shorter than the maximum context size the model can handle.
What are the key theoretical or practical benefits of utilizing your task-specific effective context limit metric in evaluating LLMs? How does it compare to previous benchmarks?
The task-specific effective context limit metric introduced in our study offers several key benefits for evaluating LLMs. Firstly, it provides a more granular understanding of model performance by determining a specific threshold of context length beyond which retrieval becomes unreliable, rather than relying on average performance metrics. This contrasts with previous benchmarks, which often focus on simpler retrieval tasks and limited context lengths, failing to capture the nuanced performance degradation observed in longer contexts. Additionally, our metric is model agnostic, based on character count rather than token count, addressing discrepancies between different tokenizers and ensuring a fair comparison across models. By leveraging detailed experimental data, our metric allows for a clearer identification of effective context limits tailored to specific tasks, enhancing the evaluation of LLM capabilities in real-world applications.
How did you validate the effectiveness of your proposed method? What datasets were used, and what metrics did you apply to assess model performance in your experiments?
We validated the effectiveness of our proposed method by conducting a series of retrieval-based long-context experiments using synthetic data, which allowed us to maintain high-quality and noise-free inputs while controlling task parameters. The datasets consisted of string serialized JSON objects containing key-value pairs, enabling us to create various tasks such as single needle, multiple needles, conditional needles, threading, and multithreading, with context sizes up to 900K tokens. To assess model performance, we applied metrics based on accuracy, specifically tracking retrieval success rates across different context lengths and task complexities. We also introduced a task-specific effective context length metric, which was derived from contour plots representing the accuracy threshold of 75%, indicating the point beyond which retrieval becomes unreliable. This comprehensive evaluation across 17 leading LLMs highlighted significant performance degradation at longer context lengths, confirming the utility of our method.
What were the main findings of your experiments, and how do they highlight the limitations of current large language models in handling long contexts? Can you elaborate on any unexpected results you encountered?
The main findings of our experiments indicate that while many leading large language models, LLMs, can perform well on retrieval tasks with shorter contexts, their performance significantly declines as context length increases, revealing a smaller effective context limit than their advertised capabilities. Specifically, we observed that models like GPT-4o maintained high accuracy even at longer contexts, while others, such as Gemini 1.5 Flash, showed accuracy dropping to nearly zero at higher context lengths. Additionally, our multi-threading tasks demonstrated that most models are thread-safe, as their performance did not degrade significantly when tracking multiple threads simultaneously. An unexpected result was the pronounced impact of thread direction on performance, with models generally performing better on forward threads compared to backward ones. Overall, these findings underscore the inadequacy of current benchmarks, as they often fail to capture the nuanced performance degradation of LLMs in real-world scenarios involving extensive context.